All right, let's look at a couple more phasor examples. Let's say we're given something like the function here. So let's say x of t equals 4 cosine 10 to the fourth t minus 40 degrees and plus 8 cosine 10 to the fourth t plus 30 degrees. All right, because those two guys have the same frequency, and I can tell they have the same frequency because the omega term here is the same, I can combine those somehow into one joint cosine expression. That turns out to be useful all the time in circuit analysis. So in other words, what I'm saying is somehow this can be rewritten as a cosine 10 to the fourth t plus phi. And my job is to figure out which values I have for a and phi. Okay? So this is also expressed as the real part of a e to the j phi e to the j 10 to the fourth t. And if I'm not sure why that is, I can expand out the inside of this expression here, and I can say this becomes a cosine 10 to the fourth t plus phi plus a j sine 10 to the fourth t plus phi. Clearly, the real part is the cosine term, which we said back here. Okay? All right. So if I look at that, and I look at the expression that I have up at the very beginning of this, I see that I've got two cosines in there. Okay? If I have two cosines, if I were to express that thing, so let's say I just said that x of t was the real part of 4e to the j minus 40 degrees times e to the j 10 to the fourth t plus 8e to the j 30 degrees times e to the j 10 to the fourth t. If I look at that and I expanded both of those things out, I'd see I get the real part of what? 4 cosine 10 to the fourth t minus 40 degrees plus j 4 sine 10 to the fourth t minus 40 degrees plus 8 cosine, so this is for the second term now, I'm expanding, 8 cosine 10 to the fourth t plus 30 degrees plus 8j sine 10 to the fourth t plus 30 degrees. All right, so I see that that guy expanded out like that. The real part of that thing, if I look, becomes simply 4 cosine 10 to the fourth t. So basically I'm looking at the expression trying to find what parts are real. That part's real and that part's real. These two terms right here are both imaginary, so I ignore those. Minus 40 degrees. And then I say plus 8 cosine 10 to the fourth t plus 30 degrees. In other words, I just wrote down both of the real parts that were inside of the brackets up here, right? So that, if I look at it, is the same as what I have at the very beginning, okay? So since these three statements here are all the same, all right, I'm going to go back and I'm going to write down that first line here again. I'm going to say this thing is the real part of 4 e to the minus j 40 degrees times e to the j 10 to the fourth t plus 8 e to the j 30 degrees e to the j 10 to the fourth t. So if I look at that, okay, I see that I can factor out in both terms. I've got this e to the j 10 to the 4th t. So it looks like I have 4e to the minus j 40 degrees plus 8e to the j 30 degrees times e to the j 10 to the 4th t. Now, my goal, I said at the very beginning, was to get something of the form shown here. So I'm almost there, because if I have here two complex numbers added together, I know two complex numbers added together are just going to become another complex number. So I can express 4e to the j minus 40 plus 8e to the j 30 as ae to the j phi. And I have that. So now what I need to do is just add 4e to the minus j 40 degrees plus 8e to the j 30 degrees. Somehow add those into ae to the j phi. Now at that point, you could expand this out using Euler's identity. Or what I did was I made use of MATLAB. Okay, so what I did was I have this line of code right here. So I move this over. Okay. All right. So focusing on this last line that I wrote, 4e to the minus j 40 plus 8e to the j 30. What I did to get that was I have this z variable here is 4 times exponential j to the minus 40. And notice I have this pi over 180. That's my degrees to radians conversion. And I do plus 8 exponential j 30 degrees times pi over 180 again to go from degrees to radians. Okay? All right, now to sort of justify that to myself. Now here's when I do the abs, remember that gives me the magnitude. When I do the angle, that gives me the angle. And because MATLAB's always in radians, I have that 180 over pi to bring it to degrees because that's what I want. All right, now down here I try to prove this to myself. Now because this time function over here, these time functions have omega equal to 10 to the 4th. It's always the case that omega equals 2 pi f or 2 pi over t, right? So I have 10 to the 4th as my angular frequency. So I have t equals 2 pi over 10 to the 4th. And then I make a delta t vector. So I do capital T, the period divided by 1,000. And then I make a time vector. So this basically gives me about 1,000 points in one period. And then what I do is I create the original signal here, right? So I have 4 times cosine 10 to the 4th t minus 40 times pi over 180. So the pi over 180 again is to convert inside the cosine expression from degrees to radians. And then in here again I have the same thing. So I have plus 30 degrees, but I multiply by pi over 180 to get it converted to radians. Then I get this, what should be the same expression here, right? This line number 10, where I say x2 is the real part of z times exponential j times 10 to the 4th times t. Okay? Now notice I don't have to do the dot multiply here because z up here is not a function of anything. It's just a number. Okay, so I'm just doing a scaling. Then I have this x3, right? In x3, so basically what I'm doing, just to be clear, right? On line number 10 here, essentially I am running this thing that I just circled here, right? This guy. And then on line 11, x3, I'm basically doing this guy right here, okay? What I'm doing is I'm saying abs of z times the cosine function, same frequency, and then I say plus the angle of z. Now here I don't have any kind of unit conversion because the angle function is naturally going to output in radians. Then I put all three of these in a figure. So I do x, which is the original expression, x2, which is the real part of the phasor, times e to the j omega t. And then I plot x3, which is the magnitude of the phasor times cosine omega t plus whatever the phi, whatever the angle is. So I plot all three of those together. So what I do is I highlight that selection, I right click on that guy, hit evaluate selection, and figure 1 pops up. And I only see one graph basically because all three of them plotted right on top of each other. So they're all completely identical. Okay? So you'll have to play around with that a little bit in the